in this example, we're going to try to determine the Fourier series coefficients corresponding to this square wave, the period for which is capital T seconds. And as you can see on your screens, the square wave stays equal to 1 for a duration from minus t to minus t1 to plus t1 seconds. And it stays 0 otherwise for the rest of the duration of the period. In order to determine the Fourier series coefficients, I'm going to use the analysis equation directly, which I've written over here. One of the things I observe next is that this integral can be over any period, anywhere, but for the ease of analysis, so when I say anywhere, it could, for example, from minus t to 0, or it could be from 0 to t, or for that matter, from t by 2 to 3 t by 2. But for ease of analysis, what I'm going to pick as the interval of integration is from minus t by 2 to plus t by 2, and that's going to make my life a little bit easier. So let me just do that. So AKs are equal to 1 upon t integral from minus t by 2 to plus t by 2 x of t e raised to the power minus j k omega naught t dt. However, I know that this square wave is equal to 1 only from minus t1 to plus t1. So, so this integral can change from minus t1 to plus t1. And so the signal is 1 during this time interval, and then I have e to the minus j k omega naught t dt. So this, therefore, if I compute that integral, so this is e raised to the power minus j k omega naught t upon minus j k omega naught, and this integral needs to be evaluated from minus t1 to plus t1, and this is equal to, therefore this is equal to 1 upon, let me pull out these k omega naught outside, so this is k omega naught times t, and over here I have e raised to the power minus j k omega naught t1 minus e raised to the power minus j, so plus j k omega naught t1 upon minus j. And from here I can change the signs. I can get rid of this minus sign here, because of which I'd have to get rid of this. This becomes plus so e raised to the power plus j minus e raised to the power. This is minus j k omega naught t1. And what you'll observe is that this thing here is actually, using Euler's identity, is actually 2 times a sine of psi, right? So what the result that I get is 1 upon k omega naught t, and this is 2 times sine k omega naught t1. And in order to simplify this further, what I observe is that omega naught t is actually equal to 2 pi by t. So therefore, this is just 2 pi by t times t, which is just 2 pi. Right, so plugging in this back here, this is therefore is sine k omega naught t1 divided by k times pi. So actually, this 2 cancels with this 2 when it goes back here. Okay. All right. So the other thing we observe is that this expression is in fact true only when k is not equal to 0. And the reason for that is because when k equals 0, not only is the numerator equal to 0, but also the denominator is 0. You would have to apply L'Hopital rule for that. That's one of the things you could do. I could encourage you to do it on your own as well. However, in order to evaluate A0, there's a much simpler approach, which just goes back and sees what this expression is. So if I just plug in k equals 0, right? If I plug in a equals 0, so what I get is a0 is 1 upon t integral from minus t1 to plus t1, and the signal is 1 for this entire iteration, and this is e raised to power j times 0, which is just 1, and therefore this is 2t1 on t. So the conclusion is the Fourier series coefficients. So the Fourier series coefficients, they are AKs is equal to 2t1 upon t whenever k is equal to 0, and this equal to sine k omega naught t1 upon k pi whenever k is not equal to 0. So this is t1, right? So that's it.